In the last segment, we talked about the value of KEQ, and that if it's a negative power of 10, that the reactants are favored. If it's a positive power of 10, the products are favored. And it should go without saying that the larger, for example, the KEQ, the more propensity it is to drive the reaction forward. The smaller the KEQ, the more propensity to go backwards. So if you have multiple KEQs or KAs or KBs or KCs, whatever it is that you want to call them, the value of that constant will tell you the extent to which they go backward or forward, or which one is going to go more forward than the other or more backwards than the other. This segment begins with the question, what happens if we want to change the direction that the reaction naturally favors? Well, that leads us to Le Chatelier's principle. And Le Chatelier's principle says that if a system at equilibrium is stressed in some way, the system will do what it can to reduce the stress. Now, this is a little bit of backwards thinking, so we have to think through what this means. So we're going to illustrate this principle with our two gentlemen in their boats. So you can think of the equilibrium as being in a boat on a nice day. It's sunny, it's not snowing or raining or anything like that. We're just happily going along. Then something disrupts the flow or the plan. So in this one, the caption says, I told you to keep the rice in a plastic bag. So presumably the rice took on water and now the boat is no longer in equilibrium. So you can envision this as if you have something that is stressing your equilibrium in this way, like for example the rice or water, that what you would do is you would try to remove that rice or the water or whatever it is that's stressing it and return it back to equilibrium. So for some examples, in this reaction, notice the double arrow. If we add more hydrogen, the reaction will want to go forward to remove the hydrogen. If we add more ammonia, the system will want to go backwards to remove the ammonia. If we cool the reaction will want to go to the side that has the heat. The side that has the heat is the backwards direction, and therefore it would go backwards. If we decrease the volume, we increase the pressure. So if we look at these moles of gas, everything here is a gas, there's 4 moles of gas on the left, 2 moles of gas on the right. So the higher pressure is normally on the left. So if we decrease the volume, we increase the pressure, we want to reduce the pressure and we'll shift to the right. In the next reaction, if we increase the temperature, we're going to want to go to the side that has less heat, less temperature. Just like if it's hot outside, we want to cool off. So the heat is on the left. So the equilibrium will shift to the right, away from the heat. If we add a catalyst, the catalyst has no effect on the equilibrium. It just helps you get there faster. If we remove SO3, we'll want to replace the SO3, so it will go backwards. If we remove O2, we want to replace the O2, so it will move forward. Please be sure as you're watching these segments of the lecture that you also go to the videos that I provided for you, extra ones on YouTube by other authors, other examples, and that you try problems in your book. There are many, many problems in your book that you should go and take a look at. Page 11. Page 11, let me turn this up back the right way, is problems to try. Okay, so the activated complex is right here, or B, and its energy is 180 kilojoules per mole. Indicate the products. The products are right here. And that is 120 kilojoules per mole. Calculate the activation energy of the forward uncatalyzed reaction. Starts at 20, ends at 180. Calculate the activation energy of the catalyzed reaction. So now we're only going up to 150. 150 minus the 20 that we started with is 130 kilojoules per mole. So remember, the catalyst doesn't shift the equilibrium, it just lowers the activation energy. And then the last question is calculate delta H. Well, we start at 20, we end at 120, so delta H is positive. It goes up. Okay, so 120 minus 20 is plus 100 kilojoules per mole. Okay, so this is going to be endothermic, which means generally speaking, this is not going to be favorable as written, even with a catalyst. Okay? Page 12. Okay, given the following. Delta H is negative, so that's exothermic. This one has a heat symbol on the left. That's endothermic. Delta H is positive. Given the following, heat's on the right, exothermic. Enthalpy will be negative. Okay, now remember Gibbs free energy, okay, that we're saying that enthalpy is the driver, but sometimes we do need Gibbs free energy, and so we have to have some kind of temperature component in order to calculate that. Okay, so you're going to want to try a few of those as well. KEQs, write a KEQ expression. Now remember your book. Many books or videos will call it a KC. And KC and KEQ for our purposes are really going to mean the same thing. So remember you have to have a double arrow, okay? So your KEQ expression, it's balanced, will be the molar concentration of H2 times the molar concentration of F2 divided by HF squared. Okay, now you can have values, okay, and you plug in and calculate. And there should be some problems like that in your book. So go ahead and give those a try. Okay? Once you calculate it, the value tells you something about which way the equilibrium naturally favors. So let's say that the equilibrium is 1 times 10 to the minus 95th. KEQ means 1 over 10 to the 95. Now there is not enough room on this page for me to write 95 zeros. So I'm just going to leave it in that form. Products, reactants. This definitely favors reactants. Okay? Now if you compare that, for example, with something that has a KEQ of 1 times 10 to the 5th, this also favors reactants, right? But this one overwhelmingly favors reactants. So you will have virtually no products here, but you'll have a few products over here. So the values of your KEQ will tell you the extent, if you are comparing one to the next, of which one would be favored over the other. Our next segment will begin with acids and bases.